All right, so answers from last night's homework. There we are. So again, just reading through these real quick. If you have questions, let me know. I'll leave them up there for a minute. Again, this is starting on the first page. Now, I only asked you to do odds, so I'm just going to read off the odds real fast. Again, all the even answers up there. So if you tried the evens, you can check your answers for those too. But again, the odds is what I asked you to focus on. That's what you had to get done for your assignment. So number 1 was 50. It was a minor arc. Number 3 was 100. It was a minor arc. Number 5 was 130. It was also a minor arc. Now, before I move on, I do want to talk quickly about where was it? No. Actually, I think I'm thinking of the next slide because I don't see the one I'm thinking of there. Yeah, no, it's on the next page. All right. Any questions on those top ones for naming? Again, minor arc is anything between 0 and 180. Semicircle is exactly 180 degrees. And then a major arc is anything from 180 degrees to 360, or between 180 and 360. All right. Then on number 7, so in that next section, we had UPQ is 130. Now, it didn't ask for a minor or major arc here, but I do want to point out on number 7, arc UPQ is actually what type of arc? UPQ. Is that minor or major? It's just a minor arc, but they use 3 letters. All right, that's technically okay. You can use 3 letters anytime to name an arc, but you normally don't see it as often if it's a minor arc. So they could have just asked for a measure of arc UQ and it would have been the same thing. It would have been the 130. But similar to an angle, you know, when you have an angle, you can use 3 letters to name an angle. If it's by itself, then you just have to use the vertex. Kind of the same thing here. When it's a major arc, you have to use 3 letters. When it's a minor arc, all you need to use is 2. All right, moving on. So 7 was 130, and these are in degrees. This worksheet didn't put a degree mark on there. Number 9 was 90 degrees. 11, 140 degrees. On 13, 230 degrees. Any questions in that section? So again, on each one of these, just remember the central angle is always equal to the intercepted arc, and then you can add the arcs when you need to, subtract the arcs when you need to. A full circle is 360. Those are things to keep in mind as you're doing those. Down on the very bottom, this was arc length. This is where the formula came in. So again, on the board, yesterday I wrote some formulas. They're still up on the whiteboard there, but arc length. Whenever you're finding the measure of the arc length, you are doing the measure of the angle or the arc over 360. So basically the fraction of the circle you're using times the circumference of the entire circle. And you can either just times it by the circumference. If they gave you a radius, then you'd use 2 pi r. If they gave you a diameter, then you do diameter times pi. But again, it is arc length. So the measure over 360 times the circumference. All right, correct answers here. On 15, you had 8.73 inches. On 17, you had 7.33 centimeters. And on 19, you had 25.13 millimeters. Are there any there that you'd like me to go over? Yes. 15? Sure. So, on 15, they gave us a radius. If they gave us a radius, we are going to use our formula that includes the radius. So again, it's the measure of 360 times our circumference formula. So we have the measure on this one for LM. If we look at the diagram over here, LM, this is 100. All right, so we're doing 100 over 360 times our circumference, 2 pi r. 2 pi, the radius here is 5. Now, really, you can just plug it straight to the calculator from there. You don't have to simplify this at all since it asks us to round to the nearest hundredth. If you want to simplify, that's up to you. This one, if you did simplify, let's see, we would have had 10 over, let's see, zeros would cancel out, 10 over 36. But those are divided by 2. We would have had 5 over 18 times 10 pi, or you can look at it. Again, didn't have to simplify, but if you did, that would reduce them because now those are divisible by 2. That's 25, 9, 5. This is our answer as an exact value. Again, plug it into the calculator to get this answer. And again, you didn't have to do any of that simplifying to get the answer as a decimal. We just took this, you can plug it into the calculator from the very start. So this first great page when we wrote, you just write that in your calculator, 100 over 360 times 2 times pi times 5, and you get your answer. As long as you plugged it in correctly, you should get the correct answer. Any other questions on those? All right. Moving right along then. Oops, that's not what I wanted to do. Clear. And here's the next set. So again, same thing. It was just odds I had asked you to do, reading through these. Now again, notice, look at number 3. It's an arc that is less than 180. They used 3 letters to do it, but it is a minor arc, right? So that is okay. Again, you just normally see it where a minor arc is going to be anything with 2 letters, but it is okay to use 3. So on number 1, that was 50 and it was minor. 3 was 130 degrees and it was minor. And 5 was 180 and it was a semicircle. Then you had on the next set, 7 was 38 degrees, 9 was 142 degrees, and 11 was 232 degrees. Any questions on those? Good? Moving right along. So on this part, you did have to find the arc length. So you're plugging into your formulas, and they're on the sideboard over there. We had 13. You had 20.94 inches. On 15, it was 19.63 meters. I have the equations right out there that you're plugged into. On 17, there was a few different answers there. So we had for A, 28.8, 104.4, 208.8, 10.8, and 7.2. And on B, it said the answer was the arc associated with 2 to 3 hours is a major arc. Minor arcs associated with the remaining categories. How did you determine those angle measures for that last question for number 17? For 17, did not have to find circumference. Again, they wanted to know the number of degrees allowed for each category. It's making a pie chart. They gave you a percentage, right? So that percentage, again, you write that percentage as a decimal. You move the decimal over 2 places. So For like the first one where it was 8%, that'd be written as 0.08. Take that and multiply it by how many degrees in a circle? 360. So 360 times 0.08 gives you the 28.8. Then you have done the 0.29 times 360 gave you the 104.4. Again, we're just multiplying each one of those percents by 360, and that's how we got those degrees for each wedge of our pie chart. So 0.29 times 360. Yep. Again, anytime you do a percent, you move that decimal place 2 spots to the left. And then on B, just to make sure you understood that one, so it said describe the arcs associated with each category. If you look at the percents, the only one that was more than half was the 58%, right? So 50% of a circle would be a semicircle. Anything greater than 50% is a major arc. So for 2 to 3 hours, you had a major arc since it was more than half the circle. All the others were minor arcs. Okay. Any other questions in that section before moving on? Yeah. 7 through 12? Yeah. Did you have a question up there? You just needed the answers. Which one? 7? Yeah. 7, 7, 7. EF. Yeah. So on that one, EF, you have 38 over here. These two, we have 2 diameters, right? Crossing. So those 2 are vertical angles. So that's 38. Then the one right next to it would have also been 38. Vertical angles. And then EF, the arc, has to be the same as the central angle. So that's also 38. Any others? All right. Let's go to the new part there. All right, so hold on. There it is. Instead of making you guys handwriting notes this time, I just am using what's on here. You don't have to really jot anything down. For the notes part, again, we'll go through a lot of examples. I want to try and go through all the examples that are on both these pages, or almost all of them. But there are a couple ideas that this section presents that are kind of important for solving for different figures when we're giving parts inside of a circle. The first one is the idea that if we have chords that are the same length, then the arcs that they're intercepting are also the same length, or vice versa. So on here, if these 2 chords are congruent, then the 2 arcs are congruent. They intersect. Or you could say it the other way around. If the 2 arcs are congruent, then the chord that intercept them would also be congruent. On this one, it's a matter of looking at it and identifying, all right, you got 2 arcs that they say are congruent. Therefore, these segments are congruent, so we can set them equal and solve. So we write an equation, we solve for x. If they ask us to find the length of the piece, then we can plug it in and find the length of the piece as well. Now, in the actual problem below, they do a lot more than just this one example. All right? So they also are using the idea that in a circle, you have how many degrees in a circle? 360. So 360 degrees in a circle. That part comes in handy for the next part. There it is. So number 1, we have 64 down here. That's the only piece that's labeled in that circle. But if this is x, this side also has to be x because those 2 chords are the same. So these 2 arcs are the same. So we know that x plus that 64 is going to give us a total of 360, right? Because that should add up to a full circle. So that's 2x plus 64 equals 360. Bring the 64 over. That's 296. Divide by 2, and x is 148. So again, there's lots of different things that they're going to ask in this section, but essentially something is set so that you have congruent pieces, that we can tell something else is congruent and should be equal in measure. And then once we do that, we should have enough information to solve for the missing parts. On C, sorry, on C, what am I saying? On 2, we have X is an angle measure. We have this is 116. Well, this line and this line are marked as congruent. So the two arcs are also congruent. Well, X is a central angle. The central angle is the same measure as its intercepted arc. So if this is 116, then X is 116. On number 3, that one's actually probably the most straightforward you can get. What's X? 82. The two lengths are the same, so the two arcs are the same. 4 is a lot like 1. They give you the entire circle we know is 360. This piece is 90. So I'm going to do it a different way, but it's essentially the same problem. We know this entire arc over here. Subtract off the 90. We're left with 360 minus 90 is 270. That's X. This is also X. So split that in half. 270 divided by 2 is 135. Get our hands on that one. So again, this one I did more algebraically. This one I just kind of reasoned out, but it's the same work. Number 5, that's a lot like our original problem. You know, the arcs are the same. So these two pieces that they gave us should also be equal. So set up an equation and solve. Subtract the 4, 14, divide by 2, and X is 7. 6 and 7 are kind of the same idea there as 5. 8 and 9, you have multiple circles. But if you have circles that are congruent, and both of these they tell us that the circles are congruent, and you have an arc that is congruent to the arc in another circle, then the chords that intersect them must be congruent. So again, it works either in the same circle or in congruent circles. So again, same up equations that we have equal pieces. And solving. 2x comes over, gives us 4x. 24, divide by 4, and x is 6. Any questions on that first page? All right. On the second page, a couple more properties. All right. Now we're dealing with some diameters, some radii that might intersect chords at right angles. If a radius or chord intersects if a radius or a diameter intersects a chord at a right angle, then is bisecting that chord. So on here, they show right angles on that diagram. So these are being bisected. So that's being bisected. This one down here is also being bisected. Now, I'm also marking these two as congruent because if the distance from the center to those is the same length, then both those chords are also congruent. So two very important properties for finding missing pieces in a circle. Again, if you have a right angle, then that chord is being bisected. Same thing down here. If they are equal distance away from the center, then those two chords are the same length. The other important property that we're going to be using a lot here is the idea that a radius, no matter where it's drawn in a circle, it's always the same. I know that's not listed on here, but I said that the other day. So in a circle, all radii are equal, right? All diameter are equal in the same circle. So on here, we are going to sometimes have to draw in a radius. They might give us the length of the radius, and that's kind of what they're showing on this next figure. So they have that dotted line in there for OD, which is acting as a radius. They gave us the length of OD, was 15. They gave us the length of CD, which was 24. So let me label this figure. Here's 15. This whole thing is 24. Well, this is being split in half, so these two are congruent. So this piece is 12, and this piece is 12. We have a triangle there, right? And it's a right triangle. They want to find OE. What do you normally use to find the missing side of a right triangle? We have two sides. We find the missing side. Going back to last chapter, that's the Pythagorean theorem. Now, do I have to use the Pythagorean theorem here? No. I got 12. I got missing side, and I got 15. This is our 3, 4, 5 times 3. The missing piece there is 9. Now again, if you don't recognize the triple, you just plug it into Pythagorean theorem. You get the same answer. So it's going to take you a little bit more work. Now I wrote these two on the board again because, like I said back when we did this section, every single section, every single chapter from this point on will have these triples mixed in somehow. I can almost guarantee that they're in almost every section, at least every chapter, and they'll definitely be on every single test or quiz. You'll have a triple mixed in some way, shape, or form. So, again, those are the ones that you should know. All right, let's do some examples because there's lots of different types of examples here. The first set, so we have that circle over there. They give us a radius is 13. All right, they say that our S is 24. Well, let's go ahead and label that piece. So here's our S. So this entire length across was 24. So that means each one of these little pieces is what? 12. Now, they told us that the radius is 13. So QR is 13. Is that going to help us solve for any of these measures? No. The only one that I have right now is the first one. We just said that this one was 12, right? But PT and TQ, how do I find either of those? Do I have enough information on that diagram right now? The only thing I didn't label was the radius, which is 13, which is this entire thing. That's these two combined. But do I have a way to solve for them individually currently, the way that diagram is drawn? No. I need to add something to it. Because in a circle, all radii are equal or congruent, right? So if I know what the radius is, which is 13, yes, QR is 13, but there's other pieces I could draw in that would help me out. What piece could I draw that would help me solve this? What would be, name a radius that I could draw right now? The letters are down for it, right? Yeah. A radius goes from where to where? From side to the middle. All right, so I already have QR drawn in. What's a radius that's not there that I could draw? Is either one of those in the center? Oh, no. Oh. All right, I could either draw RP or SR. This is P, this is circle P. This is P right here in the middle. If I draw this radius in, now we have a right triangle. Now we have a right triangle, and we know that this piece is 13, because all the radii in this circle is 13. We can now solve this problem. But you had to add that extra piece. So if you're doing a circle problem and you get stuck and you don't know where to go, try drawing in a radius, see if it helps you. Because now we have blank 12, 13. We could Pythagorean theorem. Or I should know that that missing piece is 5, because that's my 5, 12, 13. One of my triples. So now I know that that piece is 5. That was PT. This one. QT, I know the whole line from Q to P was 13. So 13 minus 5 leaves QT as 8. Again, a lot of these you're going to have to draw an extra piece. Same thing on the next set. You're going to have to draw an extra radius to solve this. Now, I will say I do not like this problem. There is, we're going to do the whole thing, but we're going to treat this piece kind of separate from the rest, because I'll tell you right now, if this was 90 and these were these, this problem could never work. All right. But we'll treat this part separate. They gave us that CD, arc CD is 90. So that's this entire arc they said is 90. So what would each of those pieces have to be? Each one of these will be 45, so that whole thing is 90. All right. Now, what I'm saying is, based on the length out here, that wouldn't be possible. So I'm treating that part as a separate problem. All right. Now we're going to use the lengths to find the other pieces. So I'm going to get rid of this stuff from here because I don't. Oh, because I can't use that. There we go. All right. So again, I'm erasing those measures because those measures don't work for the rest of this problem. All right. We have 12 and 8. So I can label those on this figure. We have 12 was the length of CD. So here's CD, right? Oh, wait. So I know 12 is the diameter. This is 12. BE is 12. So each of these little radii would be 6. CD was 8. So each of these are 4. They want us to find FD. Well, I got FD. That piece is 4. The next piece they want is AF, which is this one right here. Again, can I find AF currently? What's labeled? No. But I can draw something else in. Draw in another radius. Now I have a right triangle. That radius we already know is 6. So I have 4, I have 6. I'm missing that piece. So I'm going to set up a right. I'm going to set up the Pythagorean theorem to solve the missing side of that right triangle. C is my hypotenuse in the right triangle, so I get C squared equals A squared plus B squared. So 4 squared plus that unknown piece squared. That's 36 equals 16. Subtract 16, we get 20. Square root of 20, that's not a perfect square. But we can break it apart into 2 numbers. 4 is a perfect square. 4 times 5 makes 20. Square root of 4 is 2. So that's 2 square root of 5. So here we got x is 2 square root of 5. Now, that's not a good final answer for that one because it does say round to the nearest 100. So I should plug that into the calculator to see what it actually is. So if I take square root of 20 on the calculator, I've got my decimal answer. If you want to do that in 10, I'm just leaving it as that exact value right now. But 2 round 5 or rounded it, plug into the calculator. Number 7. On number 7, we have circle R. We say that TS is 21. So that's this whole thing is 21 over here. UV is 3x. Well, what do I know about TS and UV? Yeah, this piece and this piece, those have to be congruent because they are both 6 units away from the center. So they have to be congruent. So I can set that equal. solve it, divide by 3, and x is 7. On number 8, they tell us that CD and CB are congruent. And they tell us that GQ is represented by that, and EQ is represented by that. What is X? Well, if these two pieces are the same length, those are congruent, then these two have to be congruent. So we're setting those equal. X plus 5 equals 3x minus 6. Bring the x over, we get 2x. Bring the 6 over, we get 11. Divide by 2, 5.5. So again, in this section, there's a lot of solving, lots of little properties there. Same as yesterday, I don't want to make you do everything that's on that paper, so I'm going to have you do the odds again. So on the back side, which is pages 19 and 20, I want you doing the odds. Just like I had assigned yesterday. I didn't give you a paper? No. Yeah, yeah, shout out at that. Wow. How did I get that far? And you just, oh my God. I can't believe we just got through that whole thing and nobody stopped me.